Hello, this is Nick Andre, welcoming you to this screencast, Communicating over the Network, Chapter 2 of Network Fundamentals. In this screencast, we will explore the components necessary for communications, learn how protocols govern the communication process, and the advantages a layered model has when describing network functionality. A network is two or more end devices connected together to share resources governed by a set of rules. Resources in today's digital era could mean a voice conversation, a typed document, a video stream, and even your Facebook update. Our networks are handling more and more different types of conversations than they ever did before. Merging or converging these different conversations, that is, networks, into one large network has made the internet what it is today. Regardless of what type of conversations our networks handle, each conversation consists of three common elements: a sender, the channel to carry the message, and the receiver. At any time during the conversation, the role between the sender and the receiver can flip. The sender, in this case the message source, will encode the message to make it network friendly and use its network interface card to transmit the binary format across the channel. The receiver, in this case the message destination, will use its network interface card to capture the signal and decode the binary format back into the original message. As the complexity of our networks increase, so will our delivering techniques. In this particular example, I have 4 different end users on the same network accessing 4 different resources. User 1 is receiving a simple text message. User 2 is listening to Pandora. User 3 is watching a movie from Netflix, and User 4's web browser is displaying search results from Google. This would be a classic example of a converged network. To increase medium efficiency, each source, sender that is, has segmented their resources into smaller pieces. This will allow messages to be sent through most efficient routes, and if the need should raise, retransmit only missing pieces. Once the data is segmented into smaller pieces, intermediary devices like routers and switches will be able to multiplex the different streams of conversations together. That is to say, the data pieces from each sender are interwoven together to create a single continuous stream of data that allows for bandwidth to efficiently share amongst all users. Unfortunately, this technique adds a new level of complexity, which means more bits will need to be processed. This burden will fall onto intermediary devices as a result. Without improvements to the hardware for these devices, pieces of data may be dropped. Some users may also experience unfair treatment, or particular services may display inconsistencies in perceived quality. In networking, we call this quality of service. Once the data is segmented, a network administrator can assign priorities to each segment. This will allow certain users or services more attention. In this example, I'm giving each user equal allotment of bandwidth. In other words, each segment user 1 receives, the others receive one of their segments. However, I could change this so that user 1, 2, and 4 receives 2 segments for every 1 segment user 3 receives. This can cause inconsistencies in quality amongst users and their services. As a result, this particular technique has generated some controversy. Just research Netflix and Comcast. Instead of using sender, receiver terminology, most network administrators prefer to use the term end device to describe senders and receivers. That is because the roles of the sender and receiver can flip during the communication process, whereas the term end device will never change. By definition, an end device is any device that originates/creates the flow of data. In other words, puts the data on the medium or pulls the data off the medium. Whereas intermediary devices manage data flows, relay data signals, and/or determine pathways for data to travel. A medium is any physical channel, such as metallic wires, glass, plastic, or air, that can carry signals to deliver the message. In a nutshell, an intermediary device is any device that doesn't put or pull messages on a medium. Rather, an intermediary device can retime and retransmit a message signal from segment to segment. If need be, determine the best path a message should travel. As mentioned earlier, they can also manage the flow of data using multiplexing techniques. Although any device that doesn't place or pull messages on a medium are called intermediary devices, not all intermediary devices are the same. Each offer unique purpose when it comes to the communication process. For example, hubs and switches are used for local connection, whereas routers are used to connect networks together. IPTVs or IP phone stuff might fall under the communication server, whereas modems are used to modulate and demodulate signals from networks to networks, as well as security being firewall that analyzes traffic coming in or leaving a network. This slide illustrates two popular intermediary devices in action. A switch used to provide collision-free connection for devices on a local area network, and the router used to connect multiple networks together. In this demonstration, the switches help to retransmit and manage the flow of the data. The router helps to determine the best path a message should travel to reach the other local area network. This course highly depends on symbols as visual aids to represent network components. It is imperative that you familiarize yourself with these symbols. The items on the left can be classified as intermediary devices. Items 7, 8, and 9 are considered to be end devices. Today's cell phones can be classified as being an IP phone and therefore as being an end device. The remaining items would be examples of different forms of media. After studying the previous slide carefully, we notice our LAN diagram contains 5 end devices and 1 intermediary device, a PC, 2 workstations, an IP phone, a server, and 1 switch connecting everything together. A LAN is short for local area network. Local is a tricky word to define. In this class, a local area network is usually contained in a single geographical area, like a classroom or a building, and is administered by a single organization. Another way to describe a local area network might be on the types of services and applications it provides for the users within an organization. Notice this slide consists of 2 identical LANs that are connected together to form a wide area network, or a WAN. Typically, a WAN expands larger geographical distances and are made possible through leasing lines from telecommunications service providers. The Internet would be a principal example of a much larger wide area network connecting metropolitan area networks to form a global area network. In fact, the Internet is short for interconnected networks, or network of networks. Without some way of governing the communication process, our LANs, WANs, and GANs would be a logistic nightmare. Fortunately, engineers have developed a system illustrated by the OSI model to bring order to this madness. Networking protocols define the structure of layer-specific protocol data units. These PDUs, as illustrated by the OSI model, are as follows. Starting with the application presentation segment, we produce data. We pass the data down to the transport layer and get a PDU known as a segment. The segment is passed down to the network layer, generating a packet PDU, and finally the packet's passed down to the data link, where the packet becomes a frame. Protocols also help to outline functions necessary for communications between layers. That is to say, the presentation layer will prepare the data so the transport layer can break it up into segments. A protocol will not require that a particular hardware or software be used to accomplish this process. Just provides an outline for a developer to follow. To ensure that layers play nicely with each other, network protocols will require layer-dependent encapsulation. For example, whenever new protocol is created for the network layer, it must interconnect with the transport layer as well as the data link layer by following an outline. It does not matter what fields are created in this new protocol, as long as they are encapsulated in its own packet header, and it does not bother the segment or frame header. It also does not matter whether this new protocol is a proprietary, that is, it's owned by a company, or if it's an open protocol like IP. It just has to play nicely with the other layers. As we progress down the OSI stack, our data, in this case an email, will be encapsulated many times over until it's placed on the medium. A layer-specific encapsulation is known as Protocol Data Unit, or PDU for short, are created as an email, in this case, is passed down the stack. In this example, the email would be the data that's generated by the application, then is passed over to the transport layer. The transport layer, using its PDU, will create a segment and place the segment over to the network layer. The IP, the network layer protocol, encapsulates each segment to produce packets. Packets are then passed to the data link layer, where a network access protocol like Ethernet will encapsulate these packets into frames, and then away they go. By now you have heard me mention the OSI model a number of times, and you're probably wondering what the heck it is. OSI is short for Open System of Interconnection. I like to think of it as an organization chart that shows new employees the chain of command. In this case, computer programmers would belong to the application, presentation, and session layer, network administrators to the transport and network layer, and manufacturers and engineers to the data link and physical layer. The model also helps us understand the communication process a lot better by illustrating what layer protocols will do to data as it's passed from layer to layer. This model will become increasingly important as the semester moves on. In other words, it would be in your best interest to remember the order and purpose of each layer. Some students prefer using the following anagram to remember order. All people seem to need data processing. A for application, P for presentation, S for session, T for transport, N for network, D for data, and P for physical. When comparing the TCP/IP model with the OSI model, you will notice that the TCP/IP model is a little bit shorter. That is because the TCP/IP model decided to join a few layers together to make it easier to explain the communication process. Both models handle the same responsibilities. One just asks more from a couple of layers. These particular layers being the application and the network access layer of the TCP/IP model. The application layer of the TCP/IP model consists of application, presentation, and session layers of the OSI model. The network access layer consists of the data link and the physical layers of the OSI model. Also notice the network layer of the OSI model is known as the internet layer in the TCP/IP. Tomato, tomato. Let's bring it all back together. In this slide, I'm using the TCP/IP model as a way to review what we discussed in this video. The application layer generates the data and passes it to the transport layer to be segmented. This layer encapsulates the data by adding a header used to identify what application and service should receive this message. After port addresses are added to the header, the transport layer passes the segment down to the internet layer. This layer encapsulates the segment by adding IP addresses, both source and destination, into a new header to create a packet. After the packet is created, it is sent down to the network access layer where physical addresses are stamped into a new header. An error detection field is placed into a trailer that precedes the packet to produce what we call a frame. This frame is then transmitted across the medium until it finally reaches its destination, another end device. This device will strip the headers and/or trailers created by the sender as it passes the data up the stack. Before the data is presented to the service, the transport layer using port addresses will identify what background service, i.e. processes running on the server, the message was intended for and pass the message to the app. This concludes Chapter 2, Communicating over the Network screencast. We explored the components necessary for communicating with end devices, learned how protocols govern the communication process, and the advantage a layered model has when describing network functionality. See you in the next screencast. Take care.